talking is the whiteboard first, and then depending on time, I'll show you some things on the computer. So the next topic we're going to do is chapter 6 of the book, elliptic curves. So you should read chapter 6 rather than reading chapter, 4 next. So read chapter 6. The reason I'm doing this is that it doesn't depend on chapters 4 or 5, and it will allow us to continue pretty quickly back with some applications in cryptography, though there are many other interesting things that we'll touch on here. But it'll mean that we can talk about how number theory is used in, for example, Bitcoin pretty soon, rather than having to wait until the very end. Okay? So it'll keep the momentum we already have with looking at RSA and Diffie-Hellman and so on. However, today I'm going to mainly give you a sense of the of where elliptic curves come from and why they're of interest. And the main motivation has little to do with cryptography or Bitcoin or anything. That is something that has become a great application of elliptic curves, but I'll talk more about just the traditional number theory interest in elliptic curves today. Okay? So a very old question is solving equations over the integers. Let's just say solving one equation over z. So this is kind of this problem that Diophantus, as the name suggests, being Greek, so it must have been a very long time ago. Diophantus, thousands and thousands of years ago, did a huge amount of work on this problem. But of course, also there's things like the Pythagorean theorem, and there's Babylonian tablets that have explicit lists of solutions to an equation of this form: f of, say, x, y equal to 0, where f is a polynomial with integer coefficients in two variables. So graphically, if you imagine taking a polynomial in two variables with integer coefficients and plotting the 0 locus, you get a picture. For example, 2x plus 3y equals 0. If you plot this, you'll get a line, right? Or you can consider another example, like y minus x squared equals 0. If you plot that, you get the parabola y equals x squared. Or if you consider an example like x cubed plus y cubed equals 0, which is the Fermat equation for exponent 3. Well, I put a 0 here, so actually, I put a 1 here, actually. And to make it more like the Fermat equation, then you'd typically be asking for the rational solutions to this equation. So you kind of have a problem here, which is the input is a polynomial f, as given, just a polynomial in two variables with integer coefficients. And then the problem it generates is, what are all of the rational solutions to this equation? So here it would be, what are all the pairs x comma y of rational numbers? So x and y are both rationals. So write x comma y in Q2 such that the equation satisfies 2x plus 3y equals 0. Okay? Figure out what that set is. That's a problem. Here, you have exactly the same problem, except with a different equation. Y minus x squared equals 0. Here you have, again, the same thing, except the equation is x cubed plus y cubed equals 1. Let's throw on another example, or add another example to this list. X squared plus y squared equals minus 1. And again, you can ask for pairs of rational numbers where x squared plus y squared is minus 1. Okay, so this is the special case of Diophantine equations in the plane, because there are two variables. You can ask a similar question with a system of equations in many variables, and things just get harder and harder. For example, you might have 5 equations in 17 variables, and you could ask, is there a rational solution or not? something very complicated like that. And if there is a rational solution, find it, or find all of them in some systematic way. In general, this problem, is there an algorithm that takes as input a system of polynomial equations? So these are polynomials, that's what this means. And then tells you either yes or no, there is a solution with rational x, y, z, etc., or not. It turns out, much to everyone's surprise, that it is impossible to construct a computer program that will solve that problem. It doesn't matter about speed, there simply isn't one. There's no possible way to write a computer program that can solve that problem. This fact was proved a couple of decades ago, and it's called Hilbert's 10th problem, which is solved. So Hilbert's 10th problem solved by a Russian named Matsievich. There is no algorithm, and I'm not saying anything, the issue of speed is not relevant here. There's no algorithm at all, and it's not like quantum computers could do this. Nothing. No way you can program a computer that does this, does the following. It takes as input a bunch of polynomial equations, so f1, f2, or a bunch of polynomials, say f1, f2, etc. Coefficients in the integers, so z adjoint x, y, z, etc. And output is either yes or no, telling you whether or not there's a common solution to f1 equals f2 equals f3 equals dot 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 equals f sub n equals 0, where you have a solution over the rational numbers. So where all the numbers that you're plugging in are rationals. So a solution over Q. I'm not going to say much more about that, but it's kind of striking because it's a theorem. There really is absolutely no way to give an algorithm to solve this problem. It's a well-accepted theorem. And the proof involves embedding certain sequences of integers as, well, basically it involves embedding certain sets of numbers, namely, say, the prime numbers, but various sets of numbers as in some way involving solutions of a certain specific problem like this. And I'm not saying anything about the details. That's beyond the scope of the class, I think. But it gives you a sense that the general problem, which for thousands of years people thought about, in general, it's just not. There are systems of polynomial equations where you just cannot decide one way or the other. Even though they really do have a solution or not, you just can't decide it. There's no way to do it. You can't give one algorithm which takes as input a system of polynomial equations and outputs either yes or no, irregardless of how long you let it run. You might think you could just do something really stupid, like a bunch of nested for loops that would search for solutions. Such an algorithm isn't an algorithm because it doesn't terminate if it doesn't find any solutions. It would just sit there and run forever. So it's not an algorithm. An algorithm has to terminate. And you can't. You might say, oh well, I'll just be able to maybe decide whether that thing terminates or not. But you can't just take a bit of code and then decide whether or not it's going to terminate. There's something called the halting problem in computer science, which says you can't just. There's no algorithm that tells you whether or not some code is going to terminate. So it's very problematic. So you can search for solutions given any specific equation. You could search, like here's an example, x squared plus y squared equals -1. Are there any rational solutions? Obviously not, because when you add up two squares you get a positive number, or at least a non-negative number, not a negative number. If you run a for loop, searching for solutions, you won't find one, but your program will also never terminate. So you'll never know that there weren't any solutions. So this is hard, but for a long time people had hope that there would be a way to solve this, but that was completely squashed by Matsievich in the 70s when he proved that there's no way to do this. So, not giving up, you might restrict the problem a little bit. So instead of considering an arbitrary system of polynomial equations, maybe you restrict to special classes. For example, take only equations in two variables. So one equation in two variables. And if you want to be really, really restrictive, let's take only linear equations in one single linear equation. So instead of asking, is there an algorithm to decide whether or not there's a solution to an arbitrary system of polynomial equations, let's go to the opposite extreme and ask, is there an algorithm that will tell us whether or not a single linear equation has a solution? Okay? Question. Can you decide whether or not ax plus by plus c equals 0. This is the general form of a linear equation. There are two unknowns, x and y, and three coefficients, a, b, and c, which are all integers, has a solution. X comma y and the rational numbers, or not. Okay, any thoughts about this? Josh, you seem to have a thought.
I saw in the book, it says that if A and B and C are rational numbers,
Yeah, a, b, and c here, we might as well take everything to always be integers because you can always just scale through. A, b, and c are integers. And you're just saying that no matter what, there's always a solution. So your program takes as input this polynomial, and what does it output? Yes, there's a solution. So that would be a pretty easy program to write. It's one line long. It's easy. The only question is you have to prove it's correct. So, but you can do that because I think you're right. Linear equations always do have solutions. I mean, they just do. You just, you're just looking for a rational solution. So if you just set y equal to 0 and solve for x, that works. So it's really easy to find a solution. The answer is yes. It's a really easy algorithm. Yes. One-line algorithm. So that's good. If you take the exact opposite extreme to what Hilbert's 10th problem is about, you get an easy answer. Okay, what's the next simplest problem after this one? Three variables. Okay, let's just, that's absolutely right. 3 variables would be another simpler one. Take one equation in 3 variables, ax plus by plus cz plus d equal to 0. That's probably the next simplest one. The answer is yes. Again, it's the same thing. And then the other thing you suggested was quadratic. Okay, let's, so in any number of variables, this is easy. So let's go on to quadratic equations. So question. Can you decide whether or not ax squared plus bxy plus cy squared plus dx plus p, not b, plus ey plus f equals 0. So here are all of these letters a, b, up through f. They're all integers. Has a rational solution. First, let me ask a simpler question. Is this an interesting question compared to the one we just looked at? Yeah, it kind of is, because here's an example where you do have solutions, like x and y are both 1, that are you have solutions. Here's an example where you don't have any solutions, and they're both quadratic. So it can go either way up here. Can you decide, though? That's right, interesting. Because it can go either way. It can go either way. Either answer is possible. Okay, any ideas about how you might solve this problem? It's not like, if we did it in one variable, it would just be the quadratic formula from high school. And you would, compute the discriminant of some quadratic, and then check to see whether a number is a perfect square or not. So you could decide, like what the roots are of a quadratic. But what about here? Any ideas? And I know that looks kind of scary because I, wrote out the whole thing, but it's not really that complicated. So any thoughts about this?
Okay.
Shift and, okay, yeah, you can put it, this equation looks a little annoying, so you can, if you're working with, say, complex numbers, you could put this in some more canonical form. So right now, if you try to plot this, it's going to look like an ellipse, or maybe a hyperbola, or a circle, which is a special case of an ellipse. So you have various options for what it might look like when you plot it. And you can certainly shift it around, so maybe if it's an ellipse, it's centered at the origin. And you have to be careful when you do this, though, in that you don't introduce any square roots or anything like that. So you're only allowed to do transformations of the equation where you're replacing x and y by some rational function of x and y with rational coefficients. But you can do that, and it'll maybe make this be a slightly simpler form. However, you'll still end up with something somewhat similar to this. Like, if you just make it, I mean, basically, if you don't know whether or not there's a rational point on here, it's hard to know which sort of translation or transformation you want to do even. Yes? But you could try to factor it. So factoring it will tell you whether or not this is a reducible or irreducible algebraic curve, which, in other words, sorry, let me just say that in plain language. If this may or may not factor. It factors if and only if when you plot it, it's a union of two lines, right? If it factored as a product of two polynomials, let's call this f of xy, what would the plot look like if it factors as, say, g1 times g2 with each of these linear? And that could very well happen. That would be a really nice special case. If that happens, the plot looks like the union of the plot of two lines. And then, you know the answer. Well, either the coefficients in that factorization are rational numbers, and then you have a solution, or they're not rational numbers, and then you maybe have to work a little harder. But if it factors, which it will not in general, for example, in this one, you write it as, I think, x squared plus y squared plus 1 equals 0. That polynomial, x squared plus y squared plus 1, that doesn't factor over the rational numbers. I mean, you can factor it if you view it as a polynomial in x over polynomials in y, but then you'll have to extend by taking a square root, which you completely leave what you were looking at. So it's not really fair. Yes?
We can think about a special case. Maybe you plug in y equals 0 or x equals 0.
Sure, you could do that a whole bunch. So you have your polynomial here. And let's just say it doesn't factor, which is usually the case. Randomly, it won't factor at all. So you could plug in y equal to 0 and check to see whether there's a solution x. And that you can check with the quadratic formula. But what if there isn't a solution for every y that you plug in? You could just sit there plugging in y's all day long and not find any solutions x. Like, for example, here, that's what would happen. Every time you plug in a y, you don't find an x. So by the way, if you plotted x squared plus y squared equals minus 1 over the real numbers, what would the plot look like? I know you're not saying anything because it wouldn't look like anything. It would just be completely empty. So everybody's right. So the plot of this looks like nothing at all. Whereas the plot of this one, you can actually see it. So there's some hope. When you plot y minus x squared, you actually see something. So there's a couple of steps you can take here. One of them is you can try factoring this. And let's just say it doesn't factor as a product of two lines. If it does, then you're done. You know what to do. If it doesn't, then you can try at least plotting it over the real numbers, using all the techniques you learned in high school for plotting. You'll have to do a little work to make sure you didn't just choose the wrong ranges. But that's the sort of thing you can do with calculus. You can figure out, if there's going to be any points, you can at least maybe say something about bounding where they'll appear. And you can. If you want to plot this, you can solve for y in terms of x. So here you have y equals square root of minus 1 minus x squared. And, you can do something with this and try to plot it. So if you plot it and you see no solutions at all, then there's clearly no solutions. Done. You output no. If you do see solutions, then you have to do something else. Okay, so you see how we have something here. And I was really hand-wavy about deciding whether or not the plot is empty, but that is the sort of thing that you can make very systematic, right? Okay, let's see. I think another thing, what are the squares modulo? Let's see. So you can do something like what you do with the real numbers, plotting it, modulo p for each prime number p. It gets a little tricky because you have to worry about we're worrying about rational solutions. So you have to worry about denominators. And so you have to rewrite your equation in such a way that you throw in another variable. So you have to write it as, basically you have to throw in a z to an appropriate power. So you really write this as dxz squared plus sorry, not z squared, but z, plus fz squared equals 0. And then you can look for solutions x, y, z, where all three of x, y, and z are integers, and you don't allow them to all be 0 simultaneously. So if you change the problem slightly like that, then you can ask whether or not there are solutions modulo prime. And if there are no solutions modulo 3, then there can't possibly be any solutions to the original equation. So that's another idea, right? So let me make that precise in a simple example, hopefully. Let's see. Let's suppose a and b are integers, just to make things a little simpler. A and b are integers, and this is our equation. A x squared plus b y squared equals, or minus 1 equals 0. So if you homogenize it, that is, you make it so that it's a homogeneous polynomial by throwing in one more variable, then you can ask for solutions x, y, z, all integers instead of rational numbers. And that's a little bit nicer because then we can work modulo of prime. It's hard to reduce rational numbers, arbitrary rational numbers modulo of prime. So you can take this equation and then ask, does it have any solutions mod of prime? Maybe for specific values of a and b. So actually, just to make it a little more general, I'm going to make this a c right here. Okay, now I want to ask you, are there any a, b, and c so that you can rule out the possibility of this having solutions by working modulo of prime? So a x squared plus b y squared minus c z squared equals 0, a, b, and c integers, and then we're asking about a solution x, y, and z, also all integers, not all 0. Okay, this is a special case of this general question where I've just simplified things a little bit by throwing away these 3 extra terms. And what I'm going to try to hope to get you to have a sense for is that there's something similar to ruling out solutions to such an equation, but instead of using the real numbers, you work modulo prime. And if you've ever done, I guess, high school math contests, apparently this is a common technique for ruling out solutions to certain equations. In fact, some people claim that every Diophantine equation that you ever solve in a high school math contest or proof doesn't have a solution. You always use this technique. I don't know if that's true, but that's what I've heard. So, anyways, I think I'll just leave this hanging and I'll make a homework problem out of this. That'll probably be better. So we'll have a homework problem, which will be an example of ruling out solutions by working mod p. Okay? Because I want to get to elliptic curves today. So I'll tell you what ends up happening. It's pretty surprising and deep, but it turns out that the answer to this question is yes. There is an algorithm which will tell you whether or not any equation of this form has a solution where x and y are rational numbers. And what the algorithm involves doing is, 1, you check this irreducibility condition right here. 2, you check that you have solutions over the real numbers. And then 3, for every prime number p, you check that you have solutions mod p squared, mod p cubed, mod p to the fourth, etc. That sounds impossible because there's so many powers and so many primes. But there's an explicit computable finite list of prime powers that you have to consider, such that as long as you have solutions modulo all of those, then you have solutions modulo every possible prime power. So let me summarize this right here. So the answer is yes. Yes. There is an algorithm. And the way the algorithm works is you check your reducibility, and then you check that you have real solutions or real solutions. And then you make sure that you have for solutions modulo p to the n, modulo p to the n for all prime powers p to the n. And the amazing thing is that, well, there are two amazing things. One is that this is in fact a finite calculation due to some explicit bounds. Basically what happens is you automatically have solutions mod most primes, and then there's a finite list of primes where you might not have solutions, and you have to check explicitly for each of those. So, finite check. Doesn't look like a finite check, but it is one. And it's pretty incredible, but as long as these necessary conditions are all satisfied, then they're sufficient. Then there must be an actual rational solution, which is really weird if you think about it, because where does that solution come from? You don't actually have it in your hands at all from any of this. Like just knowing that there's a real solution here, it doesn't actually give you one. But if you have a real solution and you have a solution mod all powers of p, then you will have a solution. So all the necessary conditions, I mean, obviously if you have a solution, you'll have a real solution. If you have a rational solution, you'll have a real solution. If you have a rational solution, you have a solution mod p to the n, because you can just clear denominators and you get a solution mod p to the n for any prime power. But amazingly, things go back in the other direction. This statement is what's called the Hasse local to global principle. That's the theorem. The Hasse local to global principle. And Hasse, his last name is German, so it should suggest to you that this isn't thousands of years old. It's more like 100 years old. So. And this idea that having solutions over the reals and modulo all powers of p should give you solutions over the rationals does in fact work in some other situations. However, it immediately fails for cubic curves. There are examples of cubic curves that have a solution mod all p to the n and over the reals, but don't have any rational solutions. So unfortunately, this approach doesn't work for cubics, but it does work for quadratics. Yes?
What's the wrong time for this algorithm?
What?
What's the wrong time for this algorithm?
You know, I don't exactly know if, I don't know if, somebody asked me this recently even, and I don't know if it's known, or at least I don't know it. So this gives you an algorithm with no information about how long it takes to run. So I'm not making any statement about complexity, and I don't actually know. People try to make it fast in particular cases. And this theorem of Hasse it's just an abstract theorem. It just says, if this is true, then there's a solution. You can do this check in a finite amount of time, and if there's a solution, you can find it. Once you know there's a solution and you're confident, then you do a for loop and you'll eventually find it. And then you I guess that would give you an exponential algorithm. But there are a lot of tricks to do things more quickly in practice, which people write papers all the time on how to try to do this more quickly. Okay, so that kind of solves the situation for quadratics. Let me say a little bit more with quadratics, namely, once you know that there's a solution, what about finding all of the solutions, right? It's not enough to just have one solution or just to know there's a solution. You actually want to have it in your hands. So here there's one step, which is deciding whether or not there's a solution that has a certain complexity. And then there's another step. Once you have a solution, once you know there's a solution, you want to find it. Maybe it's enormous. By the way, there's something called Pell's equation, which kind of falls into this, and which is discussed, I think, a lot in chapter 4 of the book, which is, I think, x squared minus dy squared equals 1. And this is a quadratic equation, and you're interested in rational solutions, or integer solutions. And it's really weird, but for incredibly small d, just a couple of digits, the smallest solution in x and y can be absolutely enormous. And for even reasonably sized d, just a few dozen digits, the x and y can be absolutely ridiculously big. There's something from antiquity called the Archimedes cattle problem, which involves, it's equivalent to Pell's equation for some relatively small d. And you can prove there's a solution, but the smallest possible solution is just ridiculously large. So I just wanted to point that out, that even this fairly special class of problems, and once you know there's a solution, maybe for some theoretical reason, it might be really hard to write it down. It turns out continued fractions are super useful in this particular case. You end up computing the continued fraction expansion of square root of d, and from that you can figure out what a solution to this is. But it can be really, really, really big. So hopefully we'll get to that when we talk about continued fractions later. Okay, so I just wanted to say another thing, which is that once you know there's a solution, what about finding all of them? So finding all solutions to that. It's kind of a silly, I mean, you have to be careful what I mean by all solutions, because if there's a solution, you have to think, how many solutions are there? So the number of solutions is either 0 solutions, or there's infinitely many. Those are the two possibilities for a quadratic. An example of this, which you have surely, hopefully seen before, is the unit circle. I'm sure everyone's seen the unit circle before. So there it is. Actually, let me try a different color. So these are the coordinate axes. Here's 1. And here's our unit circle, which the corresponding equation that we're considering is x squared plus y squared minus 1 equals 0. Okay, this does have rational solutions. Here's one right here, minus 1 comma 0. And it would satisfy all these checks because it certainly has real solutions, because the plot is not empty, and it has solutions modulo every prime. You could just take this one solution and reduce it mod any prime, and you'll find a solution. So now you might wonder, what about other solutions? Are there any others? Well, of course, there's one over here, one right here, there's one over here. Are there any others? Does anybody know any other points on this curve? Yes? What? 7. Say that again? Okay. 7 over 25. 24 over 25 equals 1. Okay, so that seems plausible. If you multiply through by 25 squared, that would be 7 squared plus 24 squared equals 25 squared. I have no idea if that's right. Yeah, okay. So there's other ones, surprising points that are just sitting here. In other words, what we're asking geometrically is, if you take an equation of this form and just plot it, what rational points does it go through? Like if you look at the plane, everywhere there's lots of little tiny rational points all over the place, and we're asking which ones does the circle go through. There are infinitely many points on this circle with rational coordinates. There's one of them. Another famous one is 3/5 squared plus 4/5 squared equals 1. Which is 3 squared plus 4 squared is 5 squared. So you might recognize that as a Pythagorean triple. And if you go back thousands and thousands and thousands of years, well, about 3,000, you'll find there's clay tablets that have very big triples like this enumerated on them. So it's something that has fascinated people for quite a while. So I need to convince you right now that there's infinitely many of these. And there's a really easy argument to convince you of that. So take a straight line that goes through this point and has a rational slope. So let's plot y equals, actually I don't want to even say what the equation is yet. I just want to be a little more thoughtful. This is a straight line of slope t, line of slope t through -1, 0, and here t is a rational number. Okay? Now let's think about what just happened. This line of slope t intersects the circle somewhere else, right here. And I claim that that other point of intersection has rational coordinates, x and y. The easiest way to be convinced of that is to simply write down the equation of this line and then substitute it into the equation of the circle, and you'll end up with a quadratic polynomial. It has two roots. One of the roots is -1, and the other root is, well, it has to be rational, because everything you did involved rational numbers. The other root has to be rational, and it'll be that x coordinate right here. And then you can then plug in for y in the equation of this line, and you'll get the y coordinate. They're both rational. You're going to do this explicitly as a homework problem, so I'm not going to completely spoil it for you. Also, if you just take any rational point on the circle, like this one right here, and then make the line that goes through that rational point and this point right here, that's a line determined by two rational points, and therefore it has rational slope. So it will be one of these lines. So in fact, you have infinitely many different rational points on the circle, and they're exactly parametrized by the choices of the slope t. And if we want to throw in -1, 0, we could just throw in, say, infinity. So I took q union infinity, that would be the vertical line right here. So the lines with rational slope, or infinity, that go through the point -1, 0 are in one-to-one correspondence with the rational points in this circle. So I think that's a pretty satisfying way of finding all the rational points in the circle, because you give an explicit procedure for finding them. And when you work it out and do the details, as you'll do in a homework problem that I'll assign Wednesday, you get, as a function of t, you get the x and y coordinates right here. And you just run through different values of t, one by one, and you'll get Pythagorean triples popping out as you do this. And you get every single one guaranteed. And exactly the same idea works for any quadratic. All you have to do is, if you have a quadratic and you know it has a rational point, because it satisfies these tests, you find one rational point by any method you want, even a stupid nested for loop, and then you draw the line that goes through that rational point with rational slope, and you look at the other point of intersection on your quadratic. And by the same algebra, you'll find exactly one other point, and in that way you'll systematically be able to enumerate all rational solutions. Again, there are infinitely many, but at least you have a parametrization of them. You know exactly whether or not something is one. You can enumerate them one by one via a very simple procedure that will guarantee to hit any one eventually and never miss anything. Okay? So that's a really nice situation to be in. So we have a complete understanding of this question from the point of view of number theory. You can decide yes or no there's a solution, and if there's a solution, you can give an explicit procedure to systematically enumerate all of them. Okay? What's the next simplest question you can look at? So we've done linear and quadratic. Cubic. All right, cubic. That's the next question to look at.
So, I have a question.
Sure.
Do these methods generalize to more variables?
Sort of. This generalizes exactly to any number of variables. The Haas local to global principle is for an arbitrary quadratic form. The parameterization stuff, I never really thought about it. Probably Just never thought about it. No idea.
So like the decidability question doesn't matter if you have 10 variables.
Yep, for quadratics, you're good to go for any number of variables. If you want to read the best place I think to read a proof of this is in Sarah's book, A Course in Arithmetic. So let me write that down. Sarah, A Course in Arithmetic. It sounds very elementary, but the more elementary a number theory book sounds based on its title, the more advanced it is. So the most terrifying book in number theory probably is Vay's Basic, I think it's called like Basic Number Theory or something like that. Or Basic Arithmetic. Some very, very misleading title. But this book, it's a beautiful book and it's a great place to read about this theorem. Okay, so the next problem is question. Can you decide? So it's the same question again, except for a cubic, whether or not f of xy equals ax cubed plus bxy x squared y plus cxy squared. I don't want to scare you too much, so I'm not going to write every single thing down. Plus some constant f. This equal to 0. Where this is a cubic polynomial. You decide whether or not this has a rational solution. Yep. Thinking about football? Right, so that's the question. First, any guesses? Do you think that? So remember, in complete generality, if you want to try to take as input an arbitrary system of polynomial equations and output either yes or no, there's a theorem that you can't do it. But if you look at quadratics, there's a theorem that you can do it. So what would you like to guess about this one? Do you think there's an algorithm that will say yes or no?
Yeah.
Okay, good guess. Any other guesses? Okay, I'm going to guess one or the other. So optimistically, we'd hope that this is a special enough case that there is an algorithm. Unfortunately, first, the most natural, so this would be a nice thing to try because this makes perfect sense for any polynomial. It has nothing to do with quadratic, does it? It's like a criteria. It has to, these are necessary conditions. If you have a solution, you'll have solutions, you'll have all these conditions satisfied. Turns out, though, there are very simple cubics that you can write down that satisfy all of these conditions, but they do not have any solutions. Here's the simplest one I know of. This is not enough. 3x cubed plus 4y cubed plus 5 equals 0. That's a really nice, simple-looking equation. It's cubic. It has a solution over the reals. You can just plug in any value of y you want and solve for x. It does have a solution mod p for any prime number p. Not so easy to prove, but it's true. But even harder to prove is that it does not have any rational solutions. There's no x and y that are rational numbers that solve this. It's called the Selmer curve. And it's a counterexample to the local to global principle working for cubic curves. So this has a point everywhere, mod p to the n, and over the reals, but it does not have a rational solution. So this is a counterexample to generalizing the local global to cubics. Counterexample to local to global. Okay, so any guesses again about this question? This idea doesn't work. Maybe something else works. Can anybody think of any cubic that has a solution? Yep, from the Fermat cubic. Actually, has a stupid solution. X cubed plus y cubed minus 1 equals 0. X equals 1, y equals 0 is perfectly valid. That gives you a solution. So sometimes cubics do have solutions. Sometimes they don't. If they do have solutions, they might have only finitely many. The Fermat cubic, Fermat's last theorem, says that there's only like the really stupid solutions with x and y both equal to 1. Or sorry, one or the other equal to 1. That's it. So Fermat's last theorem is the assertion, well, the special case of that for exponent 3 says that this has only only a finite number of solutions, a very small number. But there are other cubics, which I'll show you in a minute, or rather in a lot more than 1 minute, but in 2 days, where you have infinitely many solutions. And they're huge, but they're there. So different things can happen. So I'm going to stop in a second, but I want to tell you that it is unknown by mathematicians today whether or not there's an algorithm to solve this problem. It's an open problem. And some consider it to be the most important open problem in number 3. So whether or not there's an algorithm to solve this exact question. And the Clay Math Institute problem about the Birch and Swinnerton-Dyer conjecture, if that were resolved, it would imply a solution to this problem. It would give an algorithm to solve it. Yes?
If we solve that problem, we get an A in the class?
If you give an algorithm, you will get an A in the class, and a lot more than that. You'll probably get a Fields medal. You would surely get a Fields medal. So, nobody knows. That's the solution. Or that's the answer. Nobody knows. Sure. Yes. Yeah. So it means that so if you take this equation and write it as a 3x cubed plus 4 plus 5z cubed equals 0, then you can ask, is there a solution below any prime? Let's take a prime like 7, q over 7. Is there a solution or not to this equation y7? With x, y, and z all integers, not all 0.
Came to,
And you can, I mean, that's not an obvious question. You have to, it's not clear that there is or isn't.
down my window, I got there.
Actually, just for fun, let's do it for p equals 2. A little bit easier. So then this becomes 1, that becomes 1, that's 0. So there's a solution to x cubed plus z cubed equals 0 minus 2.
Second and 43rd.
Sure, just take x to be 1 and y to be, and z to be 1, and then you add those two together, you get 0. But then you have to do as much 2 squared and 2 cubed, and it just gets harder and harder. But it is possible to decide one way or the other whether there's a solution mod p to b.
So if there's at least one like solution for p, like for this question, your equation you have 2, then 1 and 2,
Yeah.
and then we'll find the solution, which means this is
Well, what you have to have is you have to have a solution mod 2,
Entirely
and a
successful.
solution mod 3, and a solution mod 5, and a solution mod 4. Basically mod every prime power
Well, I
there is.
was,
And then it still doesn't apply
at the time that I taught.
Because it's false that doesn't have
50-50
solution
shares
to
of
rationals.
Oh, yeah.
Yeah.
But if you look
Well,
at
if you
quadratics
look
at the
instead,
statistics,
so you're looking at over there,
Or-
then
If you
having a
look at the
solution mod all prime
first of all,
powers
they stopped
implies
on them
by a deep
when they
theorem
went further
that you have
in.
solutions over the rationals.
So they
In
need
other
to
words,
set it
they
as
had already
all
figured it
prime
out.
powers and all in.
And secondly,
Yeah.
But how can n be? Oh yeah, because the fact this
Well,
price is
never
bigger
played
than
a
the
pretty
number
good defense
of
all year.
equations.
Yep.
That's it.
Okay. Thank
Yeah,
you.
something like that.